Hello, good morning. I'm Alex Black and welcome to this ASE special COVID webinar. Before I start, I would like to thank the ASE communications team who've worked with me and I think all the presenters prior to and after each presentation. So a big thank you to Angela, Catherine, Emilia and Alistair. And also a big shout out for the ASE in general. It's been a mainstay of support for me and ideas throughout my teaching career. I've been going to the conferences for the last 5 years. It's one of the most fantastic set of events you can imagine, and some of the greatest networking, as well as being the biggest subject association for science education in Europe. Okay, today's webinar is about CASE and how you can develop lessons that bridge from the CASE methodology. It's going to be split into 4 parts. The first part of about 20 minutes on cognitive readiness with up to 10 minutes questions. Second part on cognitive demand, again followed by specific questions. And then the final part will be looking at how to apply this cognitive readiness and demand and the pedagogy of CASE into other areas of the curriculum. And I'll be showing some of the bridging lessons that we've created, and that'll lead into final questions. Also, you can see the bit.ly link. You can download this presentation, so you have all the links and all the references. Okay, so to get clear, what is CASE? Well, at its minimum, you can think it's the 30 original intervention lessons, and I'm stressing that they were designed to intervene in the development of students' scientific thinking and to try to accelerate the development of their ways of thinking, this Piagetian schemata of thinking. And this was done traditionally in the first 2 years of secondary schooling, which would be year 7 and year 8 in the United Kingdom. Though there have been some variants. In Ireland, they did it across the primary secondary transition, and in some other countries, it's been done later in secondary schooling. That's the bare minimum, 30 lessons designed to develop thinking. However, it was based on many decades of research, and I'm going to give you a brief overview of some of that in terms of developing a theory of the readiness of students in their thinking and the demand of the secondary science curriculum. And this was first published in this book, Towards the Science of Science Teaching, in '81, when I was doing my PGCE at Leeds University. And people in the 19th century write about how reading The Origin of Species changed their lives. Well, this changed my teaching life. And so it's a theory that's been put into sets of lessons shown on the left, that have a readiness to start students at a lower cognitive demand and then target a higher and an even higher. And the whole idea is to stretch the cognitive demand throughout the lesson and to lead the students to stretch their thinking. Okay, so this idea of cognitive readiness, the authors of the CASE program, Philip Adey, Mike Shea, Carolyn Yates, they were particularly informed by Piaget and his description of how students go through concrete operational thinking to formal operational thinking, and they use Piagetian terminology. Now, up to 1974, and this came as a big surprise to me, the age of transition in these stages was rather over-optimistic, and we'll see some of the data about that. This was done with smaller samples, and it seemed quite biased, more advanced thinking students who were related to the researchers in the Geneva area. For instance, the fact of students from 11 to 13 moving into formal operational thinking is very, very over-optimistic. A key for me in understanding Piaget is that it gives access for me as a teacher and for teachers in general to get to know about student thinking and how student thinking affects their learning, especially of the quite strong conceptual demands of many science ideas. Now, Dylan William and John Hattie agree on very little, but from their writings that this is one thing, that if teachers and students become aware of how they're thinking and how they're learning, this is where we can have quite a big impact. So the Case people at Chelsea College, which then later moved into King's College, they worked, and they obviously had some good government funding, to change the Piagetian clinical interviews that were done around scientific phenomena and everyday phenomena. They developed these as science reasoning tasks, SRTs. They developed 7 of them, and the first 4 are the ones that I've used throughout my teaching career. In fact, just about all the students I've taught at different age groups, I've always, to begin with, the first lesson I've had them, I've used one of these SRTs. The ones with the green, you can click the hyperlink and get the whole package, the original tests, and also some scoring sheets, and also the teacher instructions of how to deliver them. And that was important, that all of the research that the CASE project did was designed that it would be helpful and produce tools that teachers could use to help their students' thinking develop and to help them get to know their students' thinking. So these are group tests that can be used, and they're very similar to a CASE science lesson. You show some phenomena and you elicit some responses from students. They validated these with the usual kind of psychometrics, internal consistency test, retest correlation. They especially wanted to make sure that these group tests were replicating the same kind of cognitive measurement as the interviews. Also, they were looking at the claim that the Piagetian theory made was that formal operational thinking develops as a unity. And they put this to the test using factor analytical models, and they were largely satisfied that they had evidence for that, except a very interesting anomaly was produced, which was combinatorial reasoning seemed to be a more advanced form of thinking than had been uncovered by Piaget and his co-workers. Now, that was a very interesting anomaly for me, later teaching IB biology, teaching genetics, for instance, where you move from monohybrid to dihybrid crosses and Hardy-Weinberg. It helped me to understand that I needed to scaffold and structure students' thinking, because combinatorial reasoning seemed to be a package of challenges. So this is where research can be highly informative for teaching practice. This is a summary, and I'll look in more detail of the results they found. And the alarm bell really is that in the final years of GCSE or O-level at this time, the mean of students hadn't yet reached formal operational thinking. Now I'm going to show you how, briefly, how one of these tasks works. This is probably the most used in research, and I've used it with thousands of students actually over my 37 years. And it's called volume and heaviness. And just to give you a taste of it, the diagrams you see in the test, the students have them as, I used a Google form in the old days, used a paper and pencil. You actually demonstrate exactly what's there. So the measuring cylinder A will be filled to 100 milliliters in front of all of the students, pointing out that you are filling it to 100. Then that will be poured into beaker X, and then you will refill beaker A. And then all of the questions tend to be categorical and discriminatory to uncover whether a student has an idea of conservation of volume. And staggeringly, many year 7 students, more than you'd think, actually think that somehow there's a change in volume taking place. And This test then has items that slowly climb cognitive demand. And for instance, same thing here, you show pouring 100 milliliters into each of these different volume empty vessels and ask them again whether they have the same amount of water. And then we're trying to explore, because these are designed, just as the clinical interviews, to elicit what concept and constructs students have in their mind to make sense of experience. And the popcorn one is you have corns, they're unpopped, and then you actually physically pop them in front of the students. And again, ask categorical questions to see if they have a concept of the conservation of material or volume. Similarly, then we get to a plasticine block that we actually show them and give them the correct answer of the block has 60 centimeters cubed when it's in a block form. And then there's a completely filled liter measuring cylinder, and then they're asked to predict how much will spill over when you lower the plasticine in on a fishing line. Then a slightly more advanced, where instead of what will spill over, it's looking at what new volume will be reached. And then this original block that anyone who conserves volume will think will have the same volume is rolled into a ball and then a cylinder. And this again discriminates those who are still struggling to have a concept of volume conservation. And then item number 10 is you have the plasticine block and an iron block of exactly the same shape and size. Pass it around the students, they can weigh each other in their minds, in their hands. And then the same question is asked, and what will happen if we lower the block of metal? Will it be more or less or the same that will spill over as with the plasticine? And then they're asked to explain their thinking. I found that usually 50% of year 7 students think that the metal block will displace more, even though it's perceptually exactly the same volume, because they have a concept of size that doesn't really differentiate between mass, volume, density. And then the later stages of the test elicit understandings of the concept of density. Often you find very, very few students are able to access this in year 7. And so it's discriminatory at the higher Piagetian level. Okay, so back to the results. That was an example of the group tests were performed with 11,000 students, a representative sample across the United Kingdom. And these are the results. And I'm going to focus on the 14 to 16 age group, which would be now the GCSE curriculum, to see that the readiness of the students at the start of that, the mean readiness, is at that kind of level, is still mid to late a concrete operational thinking, whereas the demands of that curriculum are in the formal operational area. And so we have a gap between demand and readiness. Anton Lawson in the University of Arizona produced, and you can click this link, this is a multiple choice classroom test of scientific reasoning that is very easy to administer if you can't have the time to use the group experimental tasks. It's a 2-tiered multiple choice where the students have to make a response and then make a response to an explanation of their first response.